In today's video, I'll be going to give a short introduction onto the shortest path problem and how to solve it using a step-by-step algorithm developed by Dijkstra. You can also solve it in Excel, and we'll be going through how to do that later on. So let's begin by saying what is the shortest path problem. It is a problem of finding the shortest path between two vertices, like the one you see over here in the diagram, but you can also call this nodes, such that the sum of the cost slash weights, meaning this is like the cost of going from S to A. You can imagine you are a taxi driver and you want to go from S to T, and you want to know how to minimize the cost. Due to the minimization problem, you can view this problem as a linear programming question, which is why we are able to use Excel to solve the problem. But before we go into the idea of linear programming, we need to understand how to solve this manually using this thing called the Dijkstra algorithm. So the Dijkstra algorithm is a single source, so it starts with only one source, shortest path algorithm for graphs with non-negative edge weights, meaning every edge here is non-negative values. So it's not like you go from to point A and it's -2 of your effort. You need 2 effort to go to there. So this is an example of how of a graph that works with the Dijkstra algorithm. And while there is more technical constraints which you can read online, it is most of the cases are possible to use the Dijkstra algorithm, or you can tweak it for the Bellman-Ford algorithm. As such, we will continue on how to use this algorithm to solve the question. So let's say for our problem now, we want to go from S to T. Okay? To go from S to T in this graph, we need to start off with a constraint. So what is the constraint, you might ask? Well, the first constraint is we need to plot this table over here, which is where all the vertex are. This path has been already filled up since I've already done it, and this is the cost of going from S. So you start from S to S is 0 effort, so obviously the shortest path is just S. To A, you just need 2. It can go to B, so it's 5. It can go to C, it's 4. But it cannot go to D, E, and T. So we'll just give them an arbitrary very big number bigger than all these values over here. But it may not be 100. In my case, I've used 100. Theoretically, it's infinity because every number is less than infinity. But we can just put 100 for our case here. So this is step 1. After writing all the weights, we move on to see which of the weights is the lowest. In our case, it is A. So A, because it is only effort of 2, we will take that now, and from A, so it means we have traveled from S to A, we'll see where can it go. This means it is only a one directional arrow, so it can only go to B, and to go to B now, it costs 4. So this 4 is lower than 5, so you update the table. So now it is a 4 over here. It can't go to C, so it remains the same weight. It can go to D for 7, so 2 plus 7 is 9. It can't go to E, neither can it go to F. T, I mean. So you can see how the algorithm is constantly applied. And because you have already visited A and S, you don't need to change these values for all of them anymore. So they stay the same throughout the algorithm is used. So now, from step 2, we repeat it again. You see which is the lowest. Now B and C could be the lowest, so you can choose either one. Let's say you go to B now. From B, you can spend 4 to go to D, but that's 8, which is lower, so you update it. Over here, you go 3 to go 7, so E is arrived in 7 efforts. but you can't go to T. You can go to C for 2, 2, 1, which is 5, but C is already 4 directly from S to C, so it makes no sense to apply more effort to go to C, and so the shortest path will just be from S to C, which you can see later on because it will stay the same throughout. So B remains at 4, D changes to 8, E is 7 now, T is still 100 because no one reaches T yet. So the next smallest is still B or C. You don't need to revisit B and A or S because it already been visited. So the idea is you move down the rows that is the smallest and has not been visited, which in our case is C. So from C, you can go to B, but that's 5, so you don't update it. You can go to E, that is now 8, so 7 is smaller, so you keep the 7. And you can't go to D, so you just leave the 8. And then you repeat it once more for now the smaller of the two, which is E. So from E, you can go to D for 8, but 8 is already the smallest. You can go from S to A to B to D. And then you can go to T for 2, 2, 3, 7. So that will be 7 plus 7, which is 14. So you update it to 14. And then now you see the smallest is out of D and T is D, which is 8. And so 2, 2, 4, you can go to T for 5, which makes it 13. And so that is the shortest path and minimize the cost from going to S to T. And so you can see it's a very simple algorithm, and it's using this greedy approach you can learn in computer science terms. I won't go into that because it's a more general approach. But for the algorithm, you can see it just goes through every node and you pick out the shortest path. And so you get the shortest path for every node, even though at the end you only want to know what is the shortest path to the terminal point, which is T. And this is all for applying the algorithm to solving the shortest path problem. How would you want to do this now in Excel is that a very smart group of mathematicians have come out of a formulation. So without going into very technical details, I'll run you through the basic idea and you will understand why this actually works. So the formulation is quite simple. This distance from node I to j is just representing the cost. And you can see that the final cost over here, let's just take this example T, is moving from S to A, which is just 2. So it's 2 times the, you move from S to A, go to A to B, D and E. So it's actually a summation, as you can see. So this summation is important to understand how to build the formulation. So our objective function is just this distance times this thing which is our decision variable, which is either taking a 1 or 0. If it's 1 when it is the shortest path. So now we know that S to A is part of the shortest path, so it's 2 times 1. Then A to B is part of the shortest path, then it's just 2 times 1 plus 2 times 1, and then you continue on to E. So it's 2 times 1 times plus 2 times 1 plus 4 times 1 plus 5 times 1. And so this is how we have our objective function. This is why we choose our decision variables to be this, and our distance function is just the cost function. But it must be subjected to a constraint, because you can't just go through every path and then decide how you want to do it, because you can't go backwards and stuff. So our constraint is that the starting node must always have an output of 1, because in minus, when the out minus the in, it has to be a 1. And then it has to be a -1 for the terminal point, because there's no out you're going already. Everything goes in at the end. And then all the intermediate must only go through once to make it short. So it's just go in 1, go out 1. So everything in the middle is 0 otherwise. If you don't understand it now, you can feel free to look again and pause the video to understand it better. So this is how we formulate the linear programming function, where this is our distance, decision, and objective, and subjected to the out minus in constraint. So now, with this formulation, we want to apply it into Excel. So we can see, this is how it looks in Excel. We have our distance matrix. So from S, everything else is 100, because you can't reach S any less than the supposedly starting point. Then you update all the possible weights from going from S to A, S to B, S to C minimally, and then from T everything 100, because everything goes into T. So this is called our distance matrix. And then for our solution space, it actually can be blank. And then our solution space can be blank. For our total in, it's just the sum of this column, and our total out is just the sum of this row. And then our out minus in is taking this minus this for everyone. Our relation must be equal to 1. The intermediates are all 0, and the terminal is minus 1. And then our total minimum distance, as you can see earlier, it is the sum of a product. So you just use the sum product formula over here for this matrix times this matrix down here, which is what we have written over here already. Afterwards, we click the solver as per our linear programming video that we did earlier, and for our objective function, we want to set it to this one. So we click this. We want to minimize. And for our changing variables now, it is this table. And for our constraints, you can see this table has to be all in binary, because our decision variable is only taking 1 or 0, and it is subjected to the constraints here, where the out, which is this column, you can see J17 to J23 over here equals, because our relation is equal, to this right hand side. So if you want, I can show you an example. I can delete this, and then I want to add that. My cell reference will be out minus in. This changed to equal, and my constraints now is the right hand side of the inequality, which is okay. So it's added over here. We shall just use the simplex program, and then when we click solve, all the values are appearing over here. But for Excel, one thing to note is, while the Dijkstra algorithm gives you the shortest path to every node from the starting point, while you only want to know what's the one to the terminal point, the Excel already immediately gives you the one to the terminal point when you put it in. So that's the usefulness when you want to streamline your process and make it faster, and you just want to use Excel to compute. But to understand the whole thing, actually the Dijkstra algorithm produces the result to go to every node. As you can see, the minimum cost is 13, which coincides with what we have already got in the first place. And the shortest path is from S to A, because it's 1. Now from A you go to B, B you go to D, C you don't pass through C anywhere. From D you go to T, and E you don't go through already since you reach T. And you can see this is how you do it in Excel, and I hope you have understand how to solve the shortest path problem, both manually using the Dijkstra algorithm and using Excel. That is all for the video, and thank you for listening. If you have liked the video, please do subscribe and share the video to your other friends so they can learn how to solve it on Excel and manually. Please like, share and subscribe, and leave any of your comments down in the comment sections below. Thank you.